Hello, my name is Luc van Nerom. I'm responsible for innovation management at PSI Metals. And today, together with Rafał Bacsorz from PSI Poland Data Analytics, I would like to discuss with you one of the problems of bringing AI technology, AI models, into an industrial environment, specifically the operational environment of a steel plant. One of the problems with AI models is that they tend to be looked at like black boxes, and production and process engineers do not like to work and live with black boxes because, of course, they cannot trust the behavior of this black box. We would like to discuss with you some of the techniques that can be used to break that black box nature of predictive models. PSI Metals is part of PSI AG, a software group focused on delivering solutions for the industry. PSI Metals is market leader for delivering production management solutions for the steel industry. Our solutions are based on a standard product that is delivering all required functionality in between ERP and basic level 2 automation. Typically, we are going to take over a sales order item from ERP. We are going to generate production orders and all required production steps to produce that specific product. On top of that, we are going to plan those production orders. We are going to schedule all needed production steps, material planning, and all the manufacturing execution requirements that are needed to track all the life cycle of a production order from the very beginning until the goods are leaving the plant. This standard product is based on a service platform. We call it the PSI Metals service platform, which is the foundation of how we can embed and integrate all these required production management functions into the environment of our customers. Of course, this is not only allowing us to bring our functionality to our customers, but also to integrate third-party models into the production management environment. This is exactly what we need to bring AI models into the production environment. And this can be our own PSI Metals models, but this can also be third-party models or partners models like smart steel technology or Primetals. For example, already today, standard in our product, we have an embedded business intelligence reporting, which is fully integrated in the full functionality of our production management. But of course, today we are talking about AI models and how to bring those into a production environment system. Also here, we have a full algorithm as a service and integration of whatever AI model we want to bring into the production.
Hello, thank you very much, Luke, for this introduction. My name is Rafał Bacsorz, and as Luke mentioned, I'm from PSI Poland, from Advanced Analytics team. As Luke mentioned, today we are going to break the black box nature of the predictive model. But first, let's sort of sketch why we need the predictive models. So one of the application of the predictive analytics is defect detection, which could be at the more general level understand as anomaly detection. In the steel industry, the defects can occur at any production stage. As you can see here, it could be during casting or during in the hot strip mill, pickling line, galvanizing line, etc. Everywhere we have the measurements which can break, or we have simply the places where the defect can occur. In this particular case, we will be focusing on the casting line and the data which was retrieved from the casting process. The data. In the predictive analytics, at least in the supervised learning, we have the independent variable, the set of predictors. We call it also features, and we try to couple this independent variable with some phenomenon, for example, the defect occurrence. And here in this particular case, we will be looking at the production data which came from the casting process, and this but in general case, we might have, let's say, variety of the data coming from different sources, like the chemical composition of the slab, the sensor data, the wear of rolls, etc., etc. And all this data is simply taken, prepared appropriately, and used in order to train the predictive model, where the target is, for example, the information about the defect. In order to utilize the data, in order to extract the business value from the data, we often apply the machine learning, the data-driven approaches, which are, as the name says, oriented on utilizing or consumption of the data. Here we talk about the quality prediction in the steel industry. And before going into our final and the most important part, which is the machine learning model interpretability, I would like to sketch the procedure at the general level of consideration, which allows on creating the machine learning models which are used productively. So we start from the data acquisition. We have to find the data in other systems or directly in the measurements. We simply collect the data with an assumption that we will use this data for machine learning training. But usually the data in the raw form is not suitable for machine learning. Therefore, we have to pre-process the data appropriately. It can be variety of issues that the data have. There can be missing values or outliers, or the shape of the distribution of particular feature might be, let's say, not the one we would like to have, etc., etc. So we have to first make the so-called exploratory data analysis, and we have to create a set of algorithms, and we have to fix the issues with the data. Then we have the machine learning training, where we take the data and we simply feed or throw in the data into the machine learning model. It can be random forest, decision trees, neural networks, gradient boosting, support vector machines, etc. And always in the supervised flavor of machine learning, in one hand we have the independent variable, which is the set of predictors, for example, process data or all these information that were mentioned before. And in the other hand, we have a target, a sort of target. It can be a categorical target like 0, 1, defect, non-defect. But it can also be a numerical value or numerical values. And we train the batch of models and we measure the quality in order to select the one which we are going to use in production. After that, after making this choice, we launch the model, the chosen model, to the production, and which means that we expose the model for new data. And we have to keep an eye on the, let's say, quality of the predictions or the quality of the data, because the environment evolves, and surely at some point we will draw the conclusion that the quality of the model dropped down and we have to simply retrain. In this particular case, we have taken the data from the production, the data related to the coil production, and we applied the machine learning technique XGBoost in order to create the binary classifier. So relatively simple predictive model where on input we have the data describing coils, and on the other hand we have the information about the defect. In fact, the predictive model, even though it is a binary classifier, it provides a probability, so the number between 0 and 1, the probability that this particular coil has a defect. And here we can have a look at the exemplary distribution of the data. So even though the data is related to real production, it was the subject of severe anonymization. At the end, we ended up with 500 observations, and each of them was characterized by 680 features. And the features included the physical characteristic of coils, the process data, the time series turned into this, let's say, time-independent form, and also the other information. Altogether, we used clean and fixed data frame in order to train the model. And according to good data science practices, we have splitted the data set into the training and testing set. And of course, the training set was used exclusively for the training, and the testing set was used for measuring, calculating the quality of the model. And here we can have a look at the quality. So it is not a perfect model, but still we can see that there is a significant predictive strength. The model has significant predictive capabilities. Here we have a recall and precision. I will not go into details and I will not be defining these quantities, but in principle, this information says that this model simply has the predictive strength, and we can use it for making the predictions simply. But our goal here is to introduce the machine learning interpretation. So the human beings, they do not feel comfortable with when being confronted with, let's say, a rabbit running or jumping out from the hat, like this, simple information, defect or non-defect. We would like to understand because the understanding helps us to trust this predictive model. And in order to show you how this understanding can be carried out, or how can we get an insight into the predictive model, we would like to show this library we use, DALEX. This is a dedicated library for machine learning model interpretability. And here we have the pyramid, the model exploration stack, where you can see some bunch of techniques which really allows the analyst to understand the predictive model. In principle, the interpretation of the predictive model can be done at the level of entire model. So we look, let's say, collectively at the entire model through the perspective of all the observations, for example, from the training set, or we can have a look at the particular prediction, and I'm going to show a couple of examples of this and that flavor of machine learning model interpretability. Here you can see the feature importance. So this is like a plot of features which are ordered according to their influence on the predictions. And here we can see that two of them, the feature 192 and feature 431, have a significant influence on the predictions. So this is the this general information, the machine learning model interpretability for entire predictive model. So here we do not pay our attention on particular prediction. Here we just infer what are the most influencing features from the perspective of entire model and entire data set. Here we have another technique we can use, the Shapley value. So here we look at the particular feature again, but here already we have the distribution of our observations, our coils, and the Shapley value. And the Shapley value just in a little bit simplified picture, simply compares the behavior of the model with and without particular feature, and the Shapley value is like, you know, this difference of the behavior of the model with and without this feature. And we see two plots for the feature 431 and 206, and here you can clearly see that the Shapley values, they form two groups. In the case of this feature on the left hand side, and here on the right hand side we have a little bit different picture. We might see here even three groups because of the scale. They are not well separated, but what is perhaps more important, we can see here some sort of outliers. So these are really observations that are worth looking at in, under the magnifying glass, I would say. Here we switch from this general predictive model interpretability to the in detail predictive model, in detail machine learning interpretability related to particular prediction. And here you can see two observations, two defects. In the bottom you have the total probability, which is close to 1 in both cases, and these are true positives. So these are the real defects which were classified by the predictive model as defects. And here we can see the decomposition of this probability into some terms related to particular features, right? And you can see that in both cases, these two features, these exactly the same that were shown on the feature importance plot, they contribute in largest extent. So the feature 431 and then here 192, they have the most important contributions to the probability, and the same story exactly is here. So this is, I would say, an important information. So you might simply get an insight into particular prediction. So this is not for you the 0-1 anymore. This is not the black and white information. Okay, this is a defect. You can see what were the features that were contributing significantly to the total probability, so to the final decision. Here I like to show the ceteris paribus plots. So these are simply they are related to particular features, and they simply show what is happening if we change the value of that feature within some range defined by the data. And here we see again this ceteris paribus plots for the defect cases. And the important remark is that the other features, they are kept constant. So we only look at the change of this probability when we change the value of this particular feature. And again, by looking at this, you get an additional insight into your predictive model. You can see here that quite often you have like a threshold value above which this probability changes significantly, right? So again, if you share this knowledge with the domain expert, it can be important, right? It can sort of bring to him additional, I don't know, understanding, a different perspective, because this is like a model. So usually we do not have an access to this knowledge, but by creating this predictive model and by decomposing the behavior of the predictive model, we can get really an additional insight into this domain from the perspective of the data. And I think here I'd like to finish the presentation about the model interpretability techniques, and I would like to say a few words about the root cause analysis. So in principle, when we look only at the predictive model, then of course we have to keep in mind that our landscape is limited. We look on the problems, on the defects, only through the perspective of the data. But of course, behind this, we have real phenomena which are really causing these defects. So from my perspective, when we combine this data perspective and the domain knowledge, we can really make a step towards the root cause analysis. We can, for example, pay the attention of the domain expert on the most contributing features to particular defect occurrence. And of course, the domain expert can try to understand this and try to sort of figure out why in this particular case, in this particular coil, these features, they have this particular values. There is some reality behind, and there were some industrial reasons why this process values were at this particular level, which is clearly correlated with the defect occurrences. And this one we can infer, and we can simply get this confidence from the machine learning model interpretability. I'd like to finish at the moment. I'm hoping that I shed some light on the machine learning model interpretability, and I'm hoping that at least to some extent you might be convinced that the predictive models do not have to be black boxes. Thank you very much for your attention.